All right, so continuing our look into the second derivative, and here our focus is more on what first and second derivatives together can tell us about the behavior or shape of a graph. So what I have here are two graphs, neither of which are function f. One is the derivative, that's in green, and one is the second derivative, that's in red and dashed. So first, in which intervals is f of x, which again is not graphed, and where is it concave up? Well, one of the key ideas is that a function is concave up where its second derivative is positive, which in this case is in these two intervals. And so the way I can describe this is f of x is concave up when x is less than a, whatever that a value is. It's some negative number close to 0, it seems to be. Or when x is greater than b. That's where it's concave up. So where it's concave down, well, that's where my second derivative is negative. So between a and b. So between a and b. That said, last is what's the significance of point C with regards to the graph? So point C, there's actually a few things we can say about this. Point C first is where the first derivative equals 0. That means this must be a stationary point. So I know that there is a stationary point where x equals c. Okay, that's it. There's more I can see because not only is it a stationary point, at this, when x is c, my second derivative is way up here, which is a positive number, which means the stationary point is where my function is concave up. So it's a stationary point when x equals c. I'll say f double prime at c is positive, which means the graph of f of x, I'll just say f of x, is concave up when x equals c. And if it's concave up, that means it looks something like this, but it's also a stationary point, so it must be a local minimum. So I can also say, therefore, this is a local minimum. But wait, there's more. If I look at the whole graph, in fact, that's the only stationary point for the whole function. And if I look before it, let me erase my highlighting here. My function all the way before it reaches c has a negative derivative, which means the whole time until we reach the stationary point, my function is decreasing. And then after that, it's increasing forever, which means the only way a function can be decreasing, reach a stationary point, and then increase is if it not only is a local minimum, I realize it actually must be the absolute minimum or the global minimum. So because it's of what I can piece together here. And so finally I can say, because the derivative of x is less than 0, until this point, I'll just say it must be a global minimum. And I'm just getting kind of tired of writing, but I've already kind of stated because, not only because it's less than 0 before that point, but also because after that point, it's always greater than 0. And although that's all we need, I'll just switch the Desmos here. And this is essentially the graph I gave you. And if I turn on the actual function, this is what the function looks like. So if I look here, notice again, there's that stationary point, which I can now see is a local minimum. All right, that said, let's put that away and move on. Okay, so what I have here in red is a portion of x cos x, but it's only from negative pi over 2 to 3 pi over 2. So let me kind of label that on here. So this is at negative pi over 2, and this is at 3 pi over 2. All right, so let's figure out where is this function concave up and concave down. For example, I can see around here it's concave up, but it seems to be it's definitely concave down around here. So there may be an inflection point right there. I don't want to jump to that conclusion. But then somewhere around here it becomes concave up again, which means somewhere in here is another inflection point. Well, finding those inflection points means finding where it changes from concave up to concave down, which means I need to find my second derivative. And so let's start with g prime. So g prime of x. If I look here, I have to use the product rule. So first the derivative of x, which is 1 times the cosine of x plus the other way around, x times the derivative of cosine x, which is minus sine x. So just to clean this up a bit, I get cos x minus x sine x. There's my first derivative. All right, but now if I want to see where it's concave up or down, I need a second derivative, so I need to differentiate this. Right, well, first the derivative of cosine is just minus sine of x. That's quite nice. Minus, I got to be careful here. I'm going to put square brackets around this. Differentiating this part requires the product rule, because I have a product of x times the sine of x. The derivative of x is 1 times the sine x left alone, plus the other way around, x times the derivative of sine x, which is cos x. But all this was being subtracted. So when I get rid of those brackets, I have minus sine x minus another sine x minus x cos x. So combining like terms, I have minus 2 sine x minus x times the cosine of x. All right, so there's my second derivative. So now I want to know, where is my second derivative, negative or positive? Which in this case, it's going to be far easier just to graph this. So, because it's good, let's graph this. And pay attention to where it's positive or where it's negative, or where it's above the x-axis or below. So let me go back to Desmos. And what we see here, I'll adjust my scales. The graph in red is what I gave you. The graph in blue is the second derivative, not the first derivative. So now I can see, where is it concave up? Well, anywhere my second derivative is positive, which is from the start to 0, as well as after this point here to the end, which remember was at 3 pi over 2. So everything from negative pi over 2 to 0, as well as everything after approximately 2.29 to the end of the function at 3 pi over 2. That's where it's concave up, and it's concave down in between. So let me write those things down, and then I essentially answer both parts of this question. So where is it concave up? So from negative pi over 2 to x to 0, as well as approximately 2.29 up to 3 pi over 2. And it's concave down in between those. So from 0 to approximately 2.29. And so hence I have found the inflection points. The inflection points are where it switches from concave up to concave down. And so in this point, the inflection points, I have one exact inflection point. So one's at 0, 0, and the other one is at approximately 2.29, the y value, which I would just find from the graph, which is approximately negative 1.51. Which again, since I relied on graphing here, I guess I didn't exactly say, you may be tempted to say the inflection point's at about 2.29, 0, but again, that's on the second derivative. I need to take this value of 2.28893 and put it into my original function, which I can just graph as well. In fact, I'll show you the graph of it. I thought I had it. Oh, there it is. There it is right there, right? So I put 2.2893 into my original function, and I get about negative 1.51 out. And I can, I always knew there was an inflection point around there. Now I can see where it is to a great degree of accuracy. All right, so lastly, I got this function e to the power of x over x, but only looking at positive values. Use the first derivative to determine the location of the stationary point. So I can tell there's only one stationary point, and use a second derivative test to classify it as a maximum, minimum, or an inflection point. Because again, a stationary point doesn't have to be a maximum or a minimum. So let's do some differentiating. dy dx should be fairly nice. I use the quotient rule, so the derivative of e to the power of x is e to the power of x times the denominator, minus the other way around, e to the power of x times the derivative of the denominator, all divided by x squared. So cleaning this up, I can do a few things. I can take out a factor of e to the power of x, so I get x minus 1 as a factor over x squared. That said, it says use the first derivative to find the location of the stationary point. So if I look here, my stationary point is where my first derivative equals 0. And the only way this fraction can equal 0 is if my numerator equals 0. Because again, x has to be a positive number, so the only way this can equal 0 is if e to the power of x times x minus 1 equals 0. Well, e to the power of x will never equal 0. So really, I just now need to think about, okay, where will x minus 1 equal 0? That factor. And so I can quickly see, okay, e to the power of x cannot equal 0. So therefore, when x equals 1, dy dx equals 0. So now where is that stationary point? So I can say therefore, the stationary point is at 1 comma. The y value, I just need to put this value of 1 back into the original function right here. I get e to the power of 1 divided by 1, which is e to the power of 1, which is e. So the one and only stationary point is at 1 comma e. All right, that's the first derivative. So now let's find the second derivative. So let's go look at dy dx squared. So I need to differentiate one of these. I would prefer to actually, if I look at this form right here, I have to use the product rule as well. I guess, is that really a big deal or not? Not really, but I'm going to look at this form here. I use the product rule, but I don't know. I just want to use it. It doesn't really matter. That said, if I look at what I said I'm going to look at, which is this first one, the derivative of e to the power of x is e to the power of x times x left alone plus the other way around, e to the power of x times the derivative of x, which is 1. Keep in mind what I've just done right here is the derivative of this part. Minus just e to the power of x. The derivative of e to the power of x is e to the power of x. However, that's just the derivative of my numerator. So if I look at this, I have to use the quotient rule as well. So everything there is being divided by x squared. So I now need to take all of this, everything I see right here. That is the derivative of the numerator times the denominator, which is x squared, minus the other way around. I leave my numerator alone. I'm running out of space here. I'll get my colorful brackets back in. So e to the power of x times x minus e to the power of x. Actually, I'm just going to write this the other way around. I'm going to write it as x times e to the power of x. So again, using the quotient rule, I've differentiated the numerator times the denominator left alone, minus the other way around. Leave the numerator alone and multiply that by the derivative of the denominator, which is 2x. And all of this good stuff is divided by x squared, so x to the power of 4. All right, definitely want to clean this up, which is not nearly as bad. If we look right here, notice I have e to the power of x times x plus e to the power of x, but then minus e to the power of x. So these two are going to cancel each other out. So really, in my up here, I have x times e to the power of x times x squared. Well, I might as well just realize that's just going to be x cubed times e to the power of x. So instead of giving myself extra writing, let me just go right to x to the power of 3 times e to the power of x. Over here, all of this, I have mine, if I distribute out the 2x, and keep in mind I'm subtracting a lot of things, it should come to minus 2x squared times e to the power of x plus 2x times e to the power of x, because I'm subtracting a negative 1 point. And all of this is being divided by x to the power of 4. Well, if I look at my numerator, everything has a common factor of x and e to the power of x. So let me factor that out. I'm going to take out a factor of x and e to the power of x. And if I take that all out, then I have just left x squared minus 2x plus 2, which does not factor, but that's okay, divided by x to the power of 4. And now I can cancel out one of these x's here. So making it a little bit nicer, I can write it as just e to the power of x times x squared minus 2x plus 2, which again does not factor, over x to the power of 3. Okay, there's my second derivative cleaned up. What was the point of doing this again? Use a second derivative to classify this as a maxima, minima, or inflection point. So I know there's a stationary point at 1, 3. So what I want to do now is take this value of 1 and substitute it into all my x's. Oh, that last one's on an x. And that will, all I care about is this is positive, negative, or 0. And so pretty quickly, if I substitute this in, I get e to the power of 1 times 1 squared minus 2 plus 2 over 1 cubed. And I can pretty quickly realize this is a positive number, which means if it's a positive number, that means it is concave up. And if a function is a stationary point and is concave up, that means it has to look something like this. It must be this minimum point. So now I know, using the second derivative test, that this point 1, e is a minimum. And since it's only stationary point, I know it's actually the global minimum. But I'll just say for now, it is a minimum. So therefore, 1, e is a minimum. Minimum. All right, I think I graphed this one. Let's see, I forget what I do so many times. Yeah, here's the graph, and there's that one and only minimum at 1, e. Phew, I'm right.